welcome to this lecture number 3 of the module on control systems for the course on electric vehicles. So far we have defined broadly what a control problem is, and to solve those problems we need to first understand the system and represent the system, and for a better understanding of the system we subject the system to several standard test signals and see how a system responds. Depends on, we just did analysis on first and second order systems. We looked upon how systems can behave when they are of underdamped nature, overdamped nature, critically damped, undamped, and so on. We also looked at how systems can be made faster and slower by looking at the time constants in the first order case, or even looking at the zeta and the omega n in terms of the second order systems, where we could control the peak overshoot, the settling time, and so on. And always it was a trade-off between faster response and overshoots. In this lecture we will look at two important concepts, which is one of the building blocks for control systems, that is the notion of stability, and then we will look at a little more of analysis in the terms of open loop versus closed loop systems. Okay, so let's start with the notion of stability. Again, here we are looking at linear time invariant systems. Linear systems are, as the definition goes, the systems which obey homogeneity and superposition. Time invariant systems are the ones where the system parameters do not change with time. Okay, so the notion of stability here is that a system is stable if it eventually comes back to its equilibrium state when subject to an initial condition. As an example, let me just take a fan, right, and I just say maybe perturb the fan a little bit. I try to rotate it. What happens after a while? The fan comes back to rest. That is its equilibrium position. Okay, and then a system is unstable when its output diverges without bounds from its equilibrium when subject to an initial condition. A simple example could be, we could look at it, say as a simple pendulum, for example. Let's say, okay, let me see if I can make this pen act as a simple pendulum, right? So I have a simple pendulum, so I just perturb this. So this is its equilibrium position, right? I do nothing, it also does nothing. I subject it to initial condition, it oscillates and comes back to rest. Okay, and now I just invert this. Okay, I just invert this. This is also classically called as the inverted pendulum. If I do nothing, it will always stay here. This is also an equilibrium position. What, however, makes it unstable is when I just push it a little bit, it just goes down. Right. So this is an unstable behavior. Here, from the equilibrium I perturb it, it comes back to its original position. This is stable. This, I push it a little bit, it just falls down. This is unstable. And then a system is marginally stable if it just continues to oscillate like this forever, right? So this oscillations don't die out, they just keep on oscillating. If the initial condition is here, they will exhibit, say, wider oscillations and so on, right? So that is the physics notion of stability, right? Now, how would I mathematically look at stability? I mean, each time I want to test a stability property of a system, I may not want to perturb it, right? What if it goes unstable and so on. Okay, so we'll talk in terms of signals, and largely people also associate stability to say, okay, what happens when I give bounded signals, how the output behaves. Okay, so if I look at a bounded signal is the one which is kind of has some finite magnitude beyond which it doesn't go, right? So it's the largest magnitude is measurable. So mathematically I can write or say that a bounded input signal is a signal whose magnitude remains finite over all time. So I can always find a number m below which the signal stays. In this case, the number m is 1, right? And it's always less than infinity. Also, so examples are, okay, so this is e power minus t, sine of t is also a bounded signal, e power minus t sine of t is a bounded signal, u of t is 100 is also a bounded signal. Unbounded signals, of course, it's just the counter of that. If I say that the bounded signal whose magnitude remains finite, An unbounded signal can achieve infinite magnitude, right? If I just look at e power plus t, it just increases with time, or e power plus t cos t, it oscillates and still increases with time, right? Okay, just as a teaser, you can just check if t e power minus t is a bounded signal or an unbounded signal. Okay, so the way I define now stability is the following. A system is stable if for every bounded input signal, the output is also bounded. System is unstable, conversely, if for any bounded input signal, the system response is unbounded, right. So, this is a simple example. I have a bounded input, I am generating a bounded output. What sits inside is a stable system. Unstable system, a bounded input is kind of giving me an unbounded input. You see that this signal is just going or increasing in magnitude. Okay, so now for a zero input to a system, if the system response asymptotically decays to 0, or within a decaying envelope, the system is exponentially stable, which means the examples that we saw in the first order case, right. So, the response was just e power minus t something, right. It just is bounded by an exponential curve. E power minus t cos t will also be a signal which at t equal to 0 will be something like this. It will just keep, the magnitude will just die down exponentially, that the rate of decay is exponential. And for linear time invariant system, exponential stability and BIBO stability are both same. Again, we will not really worry about where this comes and how we derive these kind of expressions. Okay, now the question that we will ask is two things I cannot do, right. I can't take a system and subject it to certain initial condition. The reason I can't do this, even though that kind of matches or it will help me test the stability of a system, but what if it goes unstable, right? What if it goes unbounded? So, I do not really want to experiment with a system to say actually that it is unbounded. I also can't really subject system to different input signals. Again, what if the output goes unbounded? However, I have a better tool of analysis. I have represented system in that form of a transfer function. So, the question that I will ask here is, can I look at the system properties, the system representation or the system transfer function, and just mathematically evaluate if the system is stable or not. Okay. So, now what does the transfer function do? The transfer function is a ratio of two polynomials, a numerator and a denominator. Now, from this transfer function, I define two things. Right? One is the poles of the system, which are the roots of the denominator, right, ds going to 0. The zeros of the system are the roots of the numerator of the system, right, or the values for which n of s goes to 0. So, in a configuration like this system will have m zeros and n poles. And for the system to be well posed, the number of zeros must always be less than or equal to the number of poles. Okay. Now, if I just look at a system of this form, a very simple illustration. So, I have a system which has m equal to 2, n equal to 3. I set the numerator to 0 and I get that the zeros are at -3 and -4. I set the denominator to 0, I get the poles are at 0 and -1 plus minus j2. Okay. So, how do I represent it in the complex plane? So, this is my S plane, the real part and the imaginary part, S and j omega. So, -1 plus j2 will be somewhere here, -3 will be here, -4 will be here, and all, if at all the poles are complex, they will be in conjugate. So, if there is a plus j2, there will always be a minus j2. They will not occur in isolation. Okay. So, what does this have to do with stability? Does it really help me understand stability? Okay. So, given any GS of this form, I can write it in terms of partial fractions. Okay. So, let us say I just take one of this element. Let us say G of S is of the form AK by S minus SK. Okay. If the pole is real, let us say Sk is A, I will write this as Ak over S minus A. Okay. Now, if Sk equal to A, so the pole lies in the left half plane when A is less than 0. It lies in the right half plane when A is greater than 0, and it lies at the origin for A equal to 0. Now, look at what is the response of this. What does it mathematically mean? So, the inverse Laplace transform of this is e power at ut. Okay, nice. Now, what is the nature of this e power at? E power at is an exponential signal. It could be exponentially decaying, it could be exponentially increasing, or it could also be constant when A equal to 0, right. When A is less than 0, the pole lies in the left half plane, and the system's initial condition will just die down to 0, indicating that it is a bounded response, right. So, one thing, right, you see carefully, pole is in the left half plane, the response is bounded, and therefore, the system is stable. It just the response does not just blow up. Okay, the next case, which is again as a consequence, we can see that if if A is greater than 0, the pole lies in the right half plane, and then my solution is Ak e power at. For A greater than 0, this will be an exponentially increasing signal, and therefore, if I just do a perturbation, which is my impulse, a perturbation or an initial condition, which I call mathematically as an impulse function, the output goes unbounded, and the system is not absolutely integrable, and therefore, the system is unstable. Okay, what if the poles are complex? This is also fine. If the poles are complex, I get a solution which is of this form. I get an exponential term. Okay, so I have the real part. So the poles are of the form minus A plus minus j b. Okay, sorry, plus A, right? This is minus, right? So the poles here will be S equal to A plus minus j b. The b sits in the sinusoidal term. This is bounded, right? So the cos of bt plus phi will be bounded between 0 and 1, or minus 1 and 1. Now, where does this A sit in? A sits in e power at. Now, signal for the system to be bounded, e power at has to be decaying. E power at will be decaying only if my A is less than 0. Okay. So, again, if the poles are conjugate, right, we look at the real part of the pole being in the negative half plane, or A must be less than 0. A must be less than 0, B can be whatever, right. For A less than 0, the poles lie in the left half plane, something like this, they will be complex conjugate. For A greater than 0, the poles lie in the right half plane, and then the system is unstable, because I look at e power at, or let us say A equal to plus 1. Let's maybe also try plotting this e power at cos t, also try plotting e power minus t cos t, and this will correspond to A less than 0, this will correspond to A greater than 0. Okay. So, this is e power minus t cos t or sin t, depends on, and this is e power t sin t. Okay. So, this is how complex poles behave, and imaginary poles. Well, if imaginary poles happens when poles are, there is no real part. So, I have earlier I had e power minus a. Okay, let me just look at here, right. So, here the solutions were e power at cos bt plus phi. If A goes to 0, I am just so if A equal to 0, e power at goes to 1, I am only looking at the sinusoidal term and some amplitude here, which means the system response will be oscillatory, or I will call this also as marginally stable. The response does not go unbounded, but it also does not settle down to a value, right. So, when if I just look at a simple pendulum without damping, At rest it is like this. If I just give it a perturbation, it will keep on oscillating like this forever. So, this is neither fully stable nor unstable, and therefore, we will call it marginally stable. Okay, so what if I have repeated roots on the imaginary axis? So, if I have roots at j omega minus j omega, I see a oscillatory response. Okay. Now, what if I have j omega minus j omega minus j omega? In this case, the system will become unstable. Of course, the math and all is here. I'll skip the part of that math. But when you have repeated roots on the imaginary axis, then the system goes to instability. Okay. Now, the conclusion here is that I can represent the system as a transfer function, and from that transfer function I can infer stability of the system, right. And then what was stability? Bounded inputs should result in bounded outputs. System will result in bounded outputs only if the impulse response is absolutely integrable. That translated to the notion of poles being on the left half plane. So, if all the roots of the characteristic equation have negative real part, the impulse response is bounded and eventually decreases to 0. Okay. So, integral 0 to infinity g tau d tau is finite and the system is stable, right. So, you can look at here, right. So, the integral of this signal has a finite value. The integral of this signal does not have a finite value. Similarly, the integral of this signal will not have yeah. So, here also if I just look at e power t, this is not an absolutely integrable signal. E power minus t, of course, is a signal which is integrable, right. It has a finite area even though the signal is infinitely long. Okay. So, if any of the root has a positive real part, say I have 10,000 roots, everybody is stable, only one guy is sitting at 0.1, then also the system is unstable. We have to be careful when there are roots on the imaginary axis. One pair of roots on the imaginary axis, j omega minus j omega, will make it marginally stable, but if I have repeated roots, it will make the system unstable. What is allowed is j omega minus j omega, 2 j omega minus 2 j omega, that is also allowed. Okay. So, so these are the larger the notions of stability, instability, and also systems which are marginally stable. And whenever we do any design, we should first make sure that the system is stable. Okay. So, the next thing that we will do is we will try to classify or look at systems as open loop and closed loop, and those notions will be slowly clear. In an open loop system, what you see, I just have the plant, I have the controller, I have a reference. The controller acts only on the input. It does not measure the output or use feedback. If I look at a fan, right, I put it at speed 1, the output is at a certain speed, that is open loop. My controller just stays at 1 no matter what. Whatever my reference is, then I switch from 1 to 2, after that nothing happens. Nobody is measuring the speed and then saying something else. Right. Similarly, if I put the speed at 3 and 4 and so on. If I am driving a car, right, how do I know that I am at 60 kilometers per hour, if I am going too fast or if I am going too slow? I have a sensor or I have a speed meter which tells me if I am overspeeding or if I am underspeeding. If I am at 80, the idea would be to slow down. If I am at 40, the idea would be to fasten up, right. So, now when I measure and take corrective actions, that's a different thing than me just putting my pedal at one point and then letting the car go. Okay. So, in the context of EVs, I can look at a fixed duty cycle PWM to the inverter, and say maybe motor speed varies with load, battery voltage and temperature, and sometimes there is no correction applied. So, whenever there is no correction applied, I will call this as an open loop system. The drawback here is that I cannot cancel out disturbances. I will just check a little bit of what this disturbance means, and then it's maybe not very useful when the plant model is uncertain or the parameters vary. Okay, closed loop system. Okay, I have a plant. There is a controller which gives a certain input to the plant. I have a Y which should match R, and then there is somebody sitting and just monitoring if Y and R are the same. Just like when I switch on the air conditioner, right? So, there is something which temperature which glows, right? That is my reference. There is something which is measuring my temperature of the room and pumping in cold air as required. And when the room temperature is equal, to the desired temperature, the control just switches off. It doesn't need to really put in, it doesn't really need to put in any extra hot air or cold air. Advantages that we will see is that this will reject disturbances, it is reduces sensitivity to parameter variations, and also we will see the power of feedback on stabilizing a system which is open loop unstable. That we will do while we design our control loops. Okay, so before we come, I'll just look at where do we see naturally occurring closed loop systems, and closed loop systems we also refer to as feedback systems. Let's say we look at the glucose in a bloodstream, and this kind of largely being talked about, and we kind of know of what people with diabetes, no diabetes, and so on. So, the objective here is that the body wants to maintain a constant concentration of glucose. Okay, when the glucose level rise immediately after a meal, insulin is generated, which causes the body to store excess glucose somewhere else. When the glucose levels are low, the pancreas secretes a hormone which has the opposite effect. So, the interplay between the insulin and glucagon helps regulate the blood sugar or the blood glucose levels. And people for whom one of these doesn't function well, you either have to have your own insulin kind of injections and so on to regulate your blood glucose level. The other example that we will talk about is, let's say I have a car, right? This car has to go at a desired some speed of say whatever Vs 60, okay, or say 60 or whatever kilometers per hour. Okay. Now, what happens if I want to go? I just give the throttle angle as input, or my accelerator as input. Right. This is some reference. Let's say it is say whatever 60 or something like that. Okay. And then when I go, two things happen. So, I just measure my actual speed and the reference speed. If I am overspeeding, I slow down. If I am going slow, I go fast, and so on. However, as I keep going on my road, I can maybe encounter an upslope or a downslope. What happens to my control in that case? As a driver, I have learnt enough to know what to do when I hit a upslope or a downslope. But when I just want the car to do whatever by itself, how does it react to situations like this? Okay. So, we will keep this simple and see, okay, what happens to it. So, the engine is modeled as a single time constant system, maybe just like a RC circuit kind, and say I will have with a gain k. So, the engine model here is k over tau s plus 1, the time constant is 20. So, I will have 20 s plus 1. Okay. So, the engine takes in the throttle angle as input and gives the speed at the output. Okay. And then now the throttle has a time constant which is, so this is my my controller, throttle controlled, and then this I just say that okay, this is much faster, and I just say that this is some number k1, it is just a constant gain and measured as in terms of degrees per kilometer per hour. Okay. Now, everything is fine as long as I can just speed up or speed down based on my reference and the actual. Things will be drastically different when I have an upslope or a downslope. Okay. So, the disturbance I will measure it as percentage elevation per unit distance, and this signal is converted into an equal throttle angle. So, I have some number here sitting some kg sitting at 100 degrees per unit percentage slope, because here I have the theta, right. This also should convert that disturbance to some angle theta. I as just for consistency of units or signals over there. I can't add some signal to some other signal and make physical meaning out of it. Okay, let us now look at steady state speed of 60 kilometer per hour. Find what is the reference. Let's start with the open loop case. Okay, and say that my k is 1.5. So my plant looks like this. I have 1.5, 20s plus 1. Then I have the throttle, which is the number 50 sits in here. Then I have the R, and what I want is the steady state speed here is 60 kilometer per hour. Okay, which means I have R times, if I call this as K, I call this as K1. R times K1 times K is 60. Okay. Now I am just looking at the steady state. So R will be 60. If I write out in the proper unit, 60 over S, and then okay, let me just do it at steady state directly, right. So I have R. R is 60 by K1 times K. So that will be 60 by 75, that is 50. So this will be 0.8, right. So in the open loop case, if the reference is 0.8, the output is 60. Okay. So kind of nothing seems to match here, right. So for a 0.8 reference, I am actually having an output of 60 kilometers per hour. Okay, what happens now in the closed loop case? I have a feedback loop here, a unity feedback. Okay, things will be slightly different now. So now I want 60 is, I just looking at the steady state, right. So so I have R K1 times K by 1 plus K1 and K. R is my unknown, I know what is K, 1.5, K1 is 50. This gives me a R of 60.8. So in the closed loop case, if this is 60.8, the output will be 60, resulting in a steady state error of is 0.8. Okay, now we will see what is how fast or how slow. That is the transient response, we are worried of that, right. How fast the system will reach the steady state. Okay. Okay, now I am looking at what time does the vehicle reach 90% of its steady state for open loop and also closed loop. Let me say that the steady state speed given was 60 kilometer per hour. Okay. Now, just because I am looking at the transients now, I will actually add the proper model times R, right. So this will be K1 K tau s plus 1, R was 0.8, this Laplace transform of that becomes 0.8 by S. I do the inverse Laplace transform, again I will skip these steps here, but we will try to understand what it means. The time signal actually now becomes 60 1 minus e power minus of t by 20, right. So if you look at this, is a first order system. I have a input and then the system just goes out to this form. Okay. Now, what is 90% of the steady state value? That is 54 is 60, 1 minus e power minus, say, let me call this as T1 by 20. This will give me T1 as 46 seconds. Good. Okay, let me compute the same now for a closed loop. What will be this for a closed loop? Okay, so now my V of S will be K1 K over tau S plus 1 plus K1 plus K. My reference in that case was 60.8 by S. V of t would be, again I'll skip the steps, this should be easy to compute, 60 1 minus e power minus t by the whole time constant would be something like 0.263. At 90% of speed, this will be 60 1 minus e power minus t1 by 0.263. Okay, so this will be, I just compute this, t1 will be 0.6. Okay, this is a big difference, right? In the open loop, it takes 46 seconds to go to 90% of the speed. In the closed loop, it's much faster. It just takes 0.6 seconds. Okay, now what will happen? Say I am at a constant speed. Now look at it intuitively before we solve the question. I am at a constant throttle speed. I hit a upslope. Okay, if it's an upslope, I am not increasing the throttle anymore. After a while, my car has to give up and just has to come to a rest, right? Because I am not giving it any extra input to overcome that height. Similarly, if I am on a downslope, if I am at the constant input, my car will just keep gaining speed. Okay. Now, the question here is calculate the upslope that will cause the vehicle to stall if it was running at 60 km per hour on a level road with reference input signal is assumed constant. Okay. So, now nothing changed, the reference is constant. Now, look at the picture here, right. What I want here is that, well, I am at a constant throttle angle, I hit a upslope, the car goes up and then stops, which means this is 0. If this is 0, the signal that comes here must be 0. The transfer function is not 0, right. So, if the input is 0, the output will go to 0. When will this go to 0? This will go to 0 when the summation of these two signals is 0, right. So, now this will be, I can call this as A times K1. So, this is a minus here, right, minus and a plus. So, if I call my reference as A, here sits K1, this is K over tau S plus 1. So, this signal that comes here is A times K1 is, now what is here? This is Kg, I will call this slope as Kg, right, this one here, Kg times d, right, which is the percentage of slope. Okay, now I know what is A is 60.8, I know what is K1, that is 50, I know what is Kg is 100, and I want to compute what is a d now. This d will now be 35.4%. Okay, when the d is 30.4%, right, at the upslope, that is 30.4% upslope will cause the vehicle to stall if it was running at 60 km per hour on level road with reference as 60.8. Okay, next one. What is the maximum, okay, there's something here, but what is the maximum permissible downslope for the vehicle to not exceed 100 km per hour if it was running at on a level road at a steady state speed of 10 km per hour? Okay, so I'll maybe quickly draw this here. I have a plant, this is my car, I have the disturbance here, a minus and a plus, I have my controller here, and all going through a negative feedback. Okay. Now, steady state speed is 10 kilometer per hour. In the closed loop setting, what we saw earlier, if this was 60, this was 60.8. Okay. Now, when this is 10, what will be this? I will give you as an exercise to compute it as in the same way. So, the reference here will be R of S will be 10.133. If this is 10.133, this will become 10. Okay, now what I want is, I want to calculate the D, the percentage slope, which will result this 10 to go to 100. Okay, now let us again look at each of these 3 signals here. So, I have now, okay, so there is 10 here, there is 10.133, there is a K1 sitting here, K over tau S plus 1 sitting here with their approximate values, there is a Kg here of 100. Okay, so first is 10.133 comes from here through a negative feedback loop, this is 10, so minus 10, this is my error signal. This error signal gets multiplied by K1 and this K1 is now with a minus. Now, my slope will be minus, right? The slope, if this is plus 30, this should be minus 30. So, this will be minus D times Kg. That is the signal which this plant observes. Okay, at the steady state I am looking at it. So, the transients will go away, times K is 100. Okay, I know K1 is 50, K is 1.5, Kg is 100. All this will give me D of 0.6% with a downward slope. Okay, good, right? So, let's quickly summarize what are the 4 things that we looked at. We compared what were the reference and actuals for the open loop and the closed loop. What we interestingly found, even though not surprisingly, is that the closed loop response is much faster than the open loop. And then if I do not take any corrective actions, my system or my car, when it goes on a upslope, just comes to a halt, right, which means somebody has to tell it to take corrective actions, but it is unable to take those corrective actions. Similarly, if it goes at downslope, where there is some time when the speed just raises from 10 to 100. What could be control problems here? The control problems could be, how do I maintain 10 kilometer per hour or even 60 kilometer per hour, no matter if I am going upslope or downslope? That can I just increase K1, K and so on? Well, you can just check that, it may not be possible, right. So, what we will see later is how to formulate control problems in a way that it will give me a desired output even in the presence of disturbances. Here disturbances come in the form of upslope and downslope. Okay. And now in the context of EVs, so I have a motor which is supplied by an inverter. The motor drives the powertrain at an angle at a given speed and so on. How does this framework of control fit into the control of EVs? And what we will see is how to design what we call as PI and D controllers to achieve the desired performance, which is both transient and steady state objectives in a general case, and also maybe some particular cases of examples that you would have done in some of the previous lectures. That's coming up in the next lecture. Thanks for listening.